Hello. All right. Please be seated, everyone. Our next speaker is Paul Smith. He's a deputy CDO of DNC, and he's a co-founder of EveryBlock. And he's going to talk about spatial data and web mapping with Python.
Can everyone hear me okay? Okay. I used to work at a company called EveryBlock, and we made our own custom maps. We did not take a solution off the shelf. We took freely publicly available data about streets, about parks, water, and along with a brand new library called Mapnik and some custom Python, and we made our own map tiles. And we did it so that we could have full control over the style, as well as do some interesting visualizations. And that was in 2008. And just this past week, two major companies announced that they were essentially doing the same thing. They were rolling their own map solutions. And I think that it's instructive that back in 2008, we thought we were opening the floodgates for a slew of custom maps to emerge. And it's been 4 years, and I think we're finally starting to see that mainstream acceptance of doing it yourself. I also think that it's indicative of the fact that working with spatial data and making maps is kind of a curveball for a lot of developers. So my talk today is about understanding the full picture of spatial data and getting comfortable with it as developers and what it looks like to work with it on a daily basis and make maps. So we're going to be heavy on concepts today. I'm also going to talk about Python libraries and applications you can use, and I'll touch briefly on some data sources. But conceptually, I think there's a lot to cover. And this is kind of don't let this list intimidate you. I'm going to go through it pretty quickly, but it should give you kind of a 30,000-foot view of what it's like to work with spatial data. And these are sort of the big categories that you'll encounter time and again. So it's good to say, okay, I know what that means, and when presented with a problem, you sort of be able to get your head around it. So spatial data are data and collections of data with multiple dimensions, usually two dimensions or 3 dimensions, and maybe sometimes 4 dimensions. You could think of 2 and 3 dimensions. That's pretty obvious. 4th dimension might be to add time. But what that means are data that are coordinates that represent a point or points in space, either on a plane, like a geometric plane, or on a globe, like the Earth. And just as a little sidebar, I think one of the reasons that there is this conceptual hurdle to working with spatial data is that we're great at working with one-dimensional data. We're great at working with non-spatial data. There's enormous amount of collective wisdom here and in the programmer community at large with working with alphanumeric data, chars, ints, floats, collections of that data, strings. And I think it gets to the fact that representationally, you've got this array of memory cells in a computer, and so you can have hello world encoded very straightforwardly, and everybody understands how to work with that and how to slice and dice it and order it and sort it. And it's because the machine, we're working at the level of the machine there. We're working with machine primitive operations and fast pointer operations. So when you think of spatial data, you can't really do the same sort of things that you can do with non-spatial or scalar data. Comparisons, well, not really. That doesn't really make sense. Like, how would you compare a point and another point like you would like a lowercase a and an uppercase a? That's pretty well understood how we compare those in programming, but not in spatial data. Ordering, not really. Ranges, kind of, sort of. So I think it's just as like a caveat, it's worth thinking of spatial data as more like objects, kind of opaque, rather than values that are represented with machine primitives. So with that aside, if we talk about the sort of the root node of spatial data, we have geometry and we have geography. And geometry is the planar, your geometry class in grade school. It's Euclidean. It's two-dimensional. It's three-dimensional x, y, maybe x, y, z. So a horizon and horizontal line, a vertical line, maybe a line coming out of the wall. And then geography, we're talking about a point on an ellipsoid. So the Earth is in a round sphere, it's bulges in the middle. We call that an ellipsoid. And a point on that ellipsoid is defined as a point of latitude and longitude, or maybe we include elevation in the third dimension. And the units of those two types of spatial data are, in geometry, it's whatever the units of that plane are. So if we've got a 4-foot by 6-foot map on the wall, well, the XY point of some arbitrary point on the wall will be in inches or feet or whatever. And in geography, we talk about degrees, either in degrees decimal or with degrees, minutes, and seconds. And if we're in the third dimension, we include elevation. That could be feet or meters or what have you. And just real quick, terminologically, features, you see this a lot in working with spatial data. Features is just a way of saying you've got some domain data, right? Like whatever you're tracking in your application. And you've got, which has some collection of attribute data, maybe a name, an email, ID, and then one or more geometries. So that collection, that bundle, is called a feature. So you could think of it as like a row in a database. And so we looked at the two types of spatial data, geometry and geography, but they're both geometries. So they both talk about objects that are points, lines, polygons. We're all familiar with that. And then the multiple versions of that. So you can have a single geometry, which is a multi-point, or a multi-string, or a multi-polygon. Or you could have a collection of geometries that's agnostic about the type. So it could be a collection of points and line strings. And then another fundamental type is, or not necessarily a fundamental type, but a common type that we work with often are bounds. It's also known as the minimum bounding rectangle, sometimes referred to as a bounding box or an envelope. You'll see those words thrown around. And these are fairly well standardized. There's a body that says, okay, these are the kinds of geometries that we're working with, we typically work with. And there's kind of a fourth one of the fundamental types, just that I throw out there because it's kind of important, a linear ring. And it's just it's a form of the line string, or line, where the last point, or the n-1 point, is identical to the 0 point, or the first point. And that just defines a closed line string. It's also known as a contour. And the reason they're important is line string, or linear rings, comprise polygons. So a polygon is an exterior, which is a linear ring, and maybe has 0 or more interior linear rings. There's also some other configurations, but that's the general idea. And then representationally, we can have Python objects that represent, so I talked a little bit about how we represent data in the machine with values, and representationally with spatial data can be anything. It can be an array, a list of points, coordinates, a tuple, a dict, where the key is x and the value is the value of that x coordinate. And then bounds can be, or a bounding box, is almost always in the case of 2 dimensions, a 4-tuple, or a list of params. In some cases, it can be a 5-point polygon. And a bounding box is just min x, min y, and max x, max y. And so in the case of the polygon, you'd have the 1, 2, 3, 4, 5 points. And then when your sort of workaday functions dealing with spatial data, one of the things you're doing is you're performing operations on that data, and that produces new geometries. So you take one polygon and another polygon, and what's the intersection that produces a new polygon. So these are just some common operations: difference, union, centroid, getting the center point of a polygon or a line string, buffer, take a point and with some amount and create a buffer around it, or a line string or a polygon, create a buffer around it. And you might recognize that the terminology looks a lot like dealing with sets, and that's no accident. The set theoretic language applies to spatial data. We're talking about sets of points and how they intersect, how they are different, how they create unions. And just some examples. You're probably familiar with this kind of thing, but if not, like, let's imagine we have polygon A, polygon B, and on the right is the output of that operation. So we have an intersection. That green diamond in the middle is the intersection of those two polygons. Here's what the difference would be, like the difference in points, and it's not, you can't swap the order. So polygon A, what is the difference with polygon B in terms of points? If you swapped it, you would have output that would be on the right-hand side, the green would be on the right-hand side in that case. So the order matters in terms of difference, like a minus operation or divide. Union, what is the union? What points are the union of these two polygons or two geometries? A centroid point for this polygon and a buffer of that centroid. So a buffer of a point creates a circle. A buffer of a line string would create kind of an ellipse, or a buffer of a polygon would create some crazy looking polygon. And then we also have operations, we have predicates, and predicates answer questions about the relationships between two geometries, two or more geometries. We ask whether polygon A contains polygon B. We ask whether line string C is within polygon D. We ask whether they intersect. We ask whether they're disjoint. And again, the set language comes into play here. And then not only are we performing operations and predicates on these geometries, we're dealing with collections of them. And here we start to get a little more practical. So how do we deal with these collections efficiently? Well, there are two big families of indexes that are unique to spatial data. The first one is the R-tree family. So this is good for all types, whether it's a point or a polygon, of geometry. And then there's the quad tree, which is best with point data only. And an R-tree, the core concept is it's a tree like a B tree, except that the bounds, each node has a bounding box, and that bounding box is the sum or the union of all of its subtrees bounding boxes. And then sort of the way that it works is that you update that tree, and each node is defined with a maximum capacity, and when that capacity is reached, it splits. And then the split is designed to minimize the overlap between the two new nodes in terms of their bounding box. So this algorithm is actually really hard to do optimally, so there are a lot of heuristics to do it, and the difference in the algorithms for splitting is what generally defines the family of R-tree variants. And so there's R-tree original, there's R-star tree, there's some others, and it's the split algorithm that really differentiates them. And then the leaf nodes are your actual objects or your features. So the way you would deal with an R-tree would be, this is what it might look if you plotted an R-tree on the top and then at the bottom a tree diagram. You can see that the bounding boxes overlap. The way you would query it is that you say, you have a probe and you say, is my probe in the bounding box of this other bounding box? If yes, then recursively descend and ask the same question. If no, move on to the next object in the node. You'll notice that, like for example, in the case of 1 and 2, their bounding boxes overlap, so you might have to search more than one subtree, and that's the reason why optimally splitting nodes is so important, because you minimize the chance that you would have to, okay, I descended down one subtree, I didn't find anything. I got to go all the way back up and do another one. Real quick, a quad tree is, like I said, best with point data, and what happens is it divides up a space into quadrants recursively. And just as a side note, if people are familiar with the geohash, it's actually conceptually equivalent to that, so I encourage you to look that up on your own. It's a way of reducing the dimensionality of like a latitude and longitude into a one-dimensional string. And it's also, which is the same concept as a space filling curve. So that's just something to think about if you're interested in exploring it further. But this is what a quad tree looks like. Again, dividing up a space recursively by quadrants. And so your probe would be, is my point within this, in this quadrant, yes or no? And then you drill down until you find the subquadrant that the thing you're looking for is in. And then index queries generally fall into these three categories. You're asking, given a point, and this is the case of the nearest neighbor, what are the k or the 50 points closest to it, or features closest to it? Given a bounding box, give me back all the features that are within it. And if I have a point query, there may be some feature that's directly at that point. So almost all of your day-to-day index queries are going to fall into these three categories. Projections. So a projection is how we go from the ellipsoid or spheroid Earth to a flat surface. And you can think of it as if you were peeling an orange and you had the skin of the orange peeled off, how would you flatten it onto a surface? That's one way of thinking about it. You would know that it doesn't quite, that you can't quite get a perfect rectangle. You've got to make some trade-offs. So there's different trade-offs with different kinds of projections. I could give a whole talk on projections alone. I'm just going to gloss over them really quickly, but that's how we go from basically the big geometric types to geographic types and vice versa. And spatial reference systems are basically ways that we hang labels onto certain projections. So projections are big parameterized lists of trigonometric operations, and a spatial reference system is a convenient way of referring to one of those. So we've got some common ones. When you're dealing with latitude and longitude, you kind of has like a default projection, which is WGS84, and that is what I call a fake projection, because it actually doesn't define how you project from latitude and longitude on a sphere to a flat surface, but it's sort of a null operation that makes it easy to store and work with data. So you'll often see that reference when you're dealing with just pure latitude and longitude. Spherical Mercator, so if people are familiar with Google Maps, this is the projection that Google Maps is in. It's often called Google Mercator, and a lot of other web maps have adopted it, Bing and Yahoo and OpenStreetMap and others. And then there are, so I'm just talking about, this is obviously not an exhaustive list, I'm just referring to a few common ones that you might see. Texas-centric Albers equal area, this is a particular favorite of mine. This produces that classic shield shape of the US, continental US, and you'll know what I'm talking about here in a second. And there are various state plane projections that are great if you're dealing with, and you need highly accurate data about a particular US state. I'm sorry, also this talk is fairly US-centric, but so conceptually a lot of these things apply to the whole world. So this is what a map might look like in WGS84 in the fake projection. You can see the US is kind of squat. This is what it would look like maybe in Google Maps under the spherical Mercator. And then here's Albers equal area map. Again, here's the shield shape of the US. So there are different, what I'm glossing over here is there are different trade-offs with working with different projections. This projection I'm showing here, it wouldn't make sense for the whole world. Spherical Mercator, the reason it was picked was it's one that works at the highest zoom level to the lowest and all over the world, and that's why it was picked. So there are trade-offs based on what the scope of your spatial data are. Real quickly, formats. Almost all of what I'm talking about here is vector data, so points and lines and vectors. And that's typically stored in, there's a few common formats. There's the shapefile, that's the sort of the granddaddy of them all. It's actually not a file at all, it's 4 files, or sometimes 3. There's a misspelling there, that should be PRJ, which would define a projection, which is sometimes optional. The data about the geometric shapes is in the shape. It's basically a pointer in the shapefile. The SHX is where the points actually live, and then the DBF would be where your attribute data is. GeoJSON is an extension of the JSON format that basically brings it into the world of features. So you have attribute data and you have geometric data. KML is, I think, familiar to a lot of people who work with Google Maps. It's a dialect or a version of XML. Real quick, WKT stands for well-known text, and it's a simple, human-readable serialization of points, lines, and polygons that you'll often see when you're working with this data. And real quick, raster. So not only are we talking about vector data, we're also talking about maps that already exist, that are already in a particular projection. And that's where you would find something like a geotiff, which would, let's say, you've got satellite data or some flyover plane that's taking orthographic photos, that those photos are going to have embedded in it the data about where that photo was taken. So, oops. So that would be where you often see that in the format called geotiff. Sorry about that. All right. Okay, so that was the big conceptual piece. That's out of the way. We can move on to some more practical, fun stuff. And then when we talk about libraries, really we're talking about, and I'm assuming kind of a Unixy platform here, we're talking about core dependencies that are almost always written in C or Java, maybe, but mostly C. And then the Python libraries that you would use kind of on top of that to make your life a lot easier, and you can work in pure Python. And those common libraries are Google OGR, which is part of the Google family. This provides functions for opening vector data, some of those formats I talked about earlier, doing transforms between projections. GEOS is a library that handles some of those operations and predicates I showed you earlier, intersection, is this point within another, that's often handled by GEOS. Proj4 is where these spatial reference systems are defined, and libspatial index is a pretty common C library for working with R-tree data, or R-tree indexes. This is by no means an exhaustive list, but here are some very common Python libraries that you'll encounter working with spatial data and maps. Shapely, R-tree, Mapnik, GeoDjango, and Cartograph. Shapely is a nice wrapper around GEOS, that library that provides you operations and predicates for manipulating geometries. So you could easily create a point using common Python syntax. You could create a buffer around that point, that's the amount of the buffer, and get the area of that point, or that new polygon that's created from the buffer. And then there's the WKT, the serialization that I mentioned earlier. And people might notice that the area of that buffered point is not 314.159. It's not exactly pi, and that's because when you buffer a point, it doesn't actually create a pure circle. It creates an approximation of a circle with a certain number of line segments. So it's almost like an octagon or something with more dimensions, or not more dimensions, but more points than that. So it's an approximation. And here's an example of working with R-tree. The R-tree Python library wraps libspatial index. And let's say that we have a collection of state features. They have like a primary key, some attribute data, and a geometry. That geometry could be a shapely geometry. We create our index, we iterate over our features, and we insert into that index that primary key and the bounding box of our feature's geometry. And then let's say we have a probe. We want to find out which state is that point in. So we create our point, and then index.intersection is that essentially bounding box query. It's an iterator, so we call list around it. And the method call is dot intersection and then a bounding box. So since we have a point, we can sort of fake a bounding box by repeating the x and the y. And then that returns 2 objects. And the reason it returns 2 objects is, remember, it's only indexed our bounding box. So even though that point is only in one, is only in the world one polygon, it's in 2 different bounding boxes. If you think about the bounding box of a state, especially some smaller East Coast states, their bounding boxes could easily overlap quite a bit. So at this point, we then, I don't show it here, but then what you would do is, oh, I do show it here. Yes. At that point, we have a list of IDs. Then we would iterate over them, right? And then for each of the, so that would be the 2 that we found doing the bounding box query. For each of those, so we've narrowed it down to 2. For each of those, then do the expensive query of, is this point contained by our geometry? And if we found it, break out of that, and we found that this point is in Maryland. So conceptually, you've winnowed down the search space quite a bit by using a bounding box search, and then you can iterate over a much smaller set. So for example, if you were working with, say, there's over 250,000 voting precincts in the US, and you wanted to find out, where do I go to vote? And I know my latitude and longitude. Well, that's a big O-N, 250,000 number of objects that you would have to search through and ask, is this point within? Using an arbitrary query, you can winnow that down to just a handful of objects, so your big O number becomes much smaller, and you can get an answer real quick. Okay, MapNick. So MapNick, like I mentioned, is a library for creating maps. And just terminologically, what we're talking about are creating basically raster images of base maps, map tiles. You might hear that word thrown around. It's written in C++. It has Python and Node.js bindings. And it has plugins for reading from spatial databases and common vector formats. And so typically what you would do if you were working in a map context on the web, you would create individual map tiles that were, say, 256 by 256 pixels in size, and each one of those is rendered individually. What happens is your browser has some JavaScript that knows the extent of your viewport, and it translates that into some real-world latitude and longitude, makes a request to your server, and then it knows to say, okay, I need the tile for this bounding box, this bounding box, this bounding box, and so those are each individual HTTP requests, and then your browser does the work of reassembling each of those individual image requests back together in your browser. So that's what happens when you use Google Maps or comparable product. And MapNick is pretty flexible. People have done some really interesting work with it. Created an 8-bit version of the city of New York. So there's a lot you can do with it. And just here's some code to create a quick map in MapNick. You would import MapNick. You create a map object, and it has a certain height and width. You create essentially styles and layers, and those styles match up with layers. So in our case, we would create a polygon style that has a certain color, a line that has a certain color, append that to our map as a style, and then let's say we're creating a map of states. We would query our spatial database. We would then say that for this layer, this certain style applies, and then append that layer to our map, and then we use an envelope or a bounding box to set the extent of our map. So we zoom to that box. We get an image object, we render it into it, and then we can return that as a byte string that you could serve directly to a client or save to a file. GeoDjango is a fantastic library that's bundled with the Django Web Framework. It basically spatially enables the ORM in Django, and it has nice standalone wrappers for GEOS, Google, OGR, GeoIP that are written in C types, nice and clean. In fact, you can even import from those wrappers without importing all of the Django machinery. So if you just need to work with spatial data, I recommend that, Shapely. Either of them can work with these data types and file formats really well. So here's an example of a spatially enabled model in GeoDjango. It's a feature, essentially. We've got some attribute data about it. And then we've got a geom, which is a multi-polygon, because states have multiple polygons. If you think about islands, or the state of Michigan has 2 polygons, the Upper Peninsula. And then we essentially make it spatially enabled by creating a different kind of manager for it, objects equals models.geomanager. So let's say we had a different model that was congressional districts, and we wanted to know which of my Django objects that are congressional districts, which of their geometries contain some point I'm interested in. So you can see that it sort of enhances the ORM's existing query syntax to make that really an easy operation. And this is a library that I just found out about this week that I think is pretty new. It's only been worked on for a couple of months. It's called Cartograph. And it's a library and a command line interface that essentially takes as input shapefiles and a little bit of configuration and outputs an SVG file. And this is really interesting because when you're working with spatial data and trying to put it on the web, there's kind of a dance that you need to do about what's your base map and what's your feature overlay data. And this kind of bakes it, so it would be really cool for like news applications and other sort of like one-off applications where you need to create like a nice looking base map and some other kind of data visualization on top of it in SVG, which is a very efficient format. You can style it with CSS. You can add behavior with JavaScript, like the D3 library or what have you. So it's really exciting. The developer of it has created some beautiful maps in a showcase. So I was just sort of blown away by it, and I thought I'd include it. Here's the configuration that you would include. It's just some JSON to make. I just did this in like 5 minutes. This configuration creates this map, pretty easy. And that's an SVG file you can load in your browser and include in another web page. Okay, real quick. So there's a couple of applications that you might be interested in. Tile stash. So I talked earlier about the mapnik and how it renders individual tiles that are sent to the browser by separate HTTP requests. Tile stash is the thing that kind of handles that. IPython. New version of IPython has inline, has a graphical console and inline plotting that you can marry with spatial data to create interactive console visualizations. QGIS is an exciting desktop application I'll talk about in 1 second. Okay, Tile Stash. This is a tile server. It serves rendered mapnik tiles, so you can import mapnik and point browsers directly at it. You can serve pre-rendered tiles, vector data, and will also cache out to S3 or whatever cache backend you want to make subsequent loads that much more efficient. It's just a WSGI application, so it's really easy to get to work with. IPython. New versions, like I mentioned, have a Qt console. So if you're working with Shapely, check out a library called Descartes from PyPy, and you can get inline plots using the matplotlib syntax of your geometric objects. So this is really exciting. This is how you invoke it, and then you can just do pretty straightforward commands to these are the intersection graphs that I showed you earlier. I just did that with the IPython Qt console. QGIS, this is a desktop application. It's cross-platform. It rivals ArcGIS and MapInfo in terms of functionality. It's open source, GPL, and you can add layers to it from your shapefiles, from spatial databases. You can do all sorts of visualizations and spatial analysis. And it works with Python. You can write plugins to extend it that can do whatever you want, from statistical analysis to nearest neighbor, whatever kind of extension you need, you can write Python for. Real quick, some data sources that you might want to examine to get to work with. And again, US-centric caveat here. The US Census provides freely available data from something called Tiger Line. This is streets, congressional districts, county boundaries, states, just an enormous, invaluable wealth of freely available data. National Atlas, if you need like shorelines and water features, it's a great resource. OpenStreetMap is, when I showed you earlier, Foursquare and Apple are converting to these different maps. Most of those maps are built using OpenStreetMap, which is a collaboratively edited streets database, which is kind of an amazing thing. And you can often find data from your state and local GIS departments. They're paid by our tax dollars. They have great data. They're often willing to share it, so I would check that out. I left out a lot in this talk. There's so much to talk about when it comes to this topic, including spatial databases. I didn't get into PostGIS, which I think is the best out there. It spatially enables PostgreSQL database. Also working in your browser with JavaScript, that's where a lot of the action happens. These are some of the libraries you might use. And then things have gotten a lot better on the map design front, and working interactively with design and maps. And this is not a Python application, but I thought I'd mention it anyway. TileMill, great application for seeing the designs of your maps before you render them. So real quick, I wanted to issue a challenge to you all. Based on some of the information I gave you today, I'd like you to ask, like, who is my congressman? Can I write an app to find out who my congressman is? And you could do this by downloading congressional districts and states shapefiles from Tiger Line, US Census. The Sunlight Foundation has an API to get the names of those representatives that are in those congressional districts, and then use a Google Maps geocoder or your HTML5 geolocation in browser to get a point of where you're at. So just to give you a hint of how you might do this, I would build an R-tree index. I would query for all congressional districts where that point that we found from geocoding is within, and then loop over the result set to find the one and only one congressional district that point is in, and then return the name of the congressman. And with that, I'm pretty much wrapped up and ready to take some questions. Everybody's already a GIS expert, so there's no questions. Good.
What would be a good general purpose tool for someone who doesn't know what they're doing? And but in particular, when I've approached it before, I've been able to get hold of some shape files, but I can't translate them from one to the next. And translating shape files seems to be a black art.
The question is, how do we translate between different formats? I would check out something called the Goodle, so GDAL, I talked about a little bit earlier. There's a collection of Unix binaries that, like OGR to OGR, OGR info, that is basically like a Swiss Army knife for converting between formats, doing projections. There's just a lot you can do. You could say, like, I've got this huge data set, some huge shapefile. I only care about some small bit of it, so extract that part for me. So I would check that out.
Hey, maybe you could speak to the differences between R trees and quad trees, in terms of like range queries and point queries and so forth. It seemed like you kind of glossed over that.
Sure. So an R tree, if you know that your data set is going to contain not just points, but also lines, polygons, maybe multiple versions of those, then really R tree is the only way to go because it works by the bounding box. If you know that your data set is all points, and it's always going to be all points, then a quad tree is a fine substitute. In terms of performance, the quad tree is probably going to beat it if it's pure point data on both sides. But in terms of trade-offs, it really comes down to what are your geometry types of your application.
Hi. So I've got a little experience trying to develop mobile dashboards that are map-based, and the initial approach was to send all the data to the client. So you very quickly end up with megs of data on the client in JSON or whatever, GeoJSON, and trying to do it in a web map. So do you have any best practices or know of any libraries that help you optimize how much data you're going to send from server to client, depending on the kind of, does that make sense?
Yeah, sure. It's a really hard problem. So there are a couple of things you could do. One is oftentimes the serialized representation of the GeoJSON objects, the geometries, has way more precision than you need for your application. So often if you look at the source of it, you might see a decimal point and then like 10 or 12 places after that. And you don't need all of that. Like 3 decimal places is I think like 6 meters of accuracy or something like that. So you could post-process the data before it's sent to the client to strip that out. And that'll reduce the file size. Now if you're using gzip, you might not get that much of a difference if you're using gzip encoding at your web server level. Other ways to do it might be this is kind of tricky, but can you paginate the results in a way? Like can you start with a smaller bounding box that may be smaller than the actual viewport and return that set, and then expand the viewport out, successively send back several responses to the client that load without blocking. That's one way to do it. But another problem you're going to have is the more objects that you have in the client, then you're going to get poor performance because it's tracking all these vertices. So another suggestion I would have would be to look at simplification. So simplification takes a geometric object and removes points that maybe not be necessary for display, but keeps the topographic shape the same.
Is that libraries?
Yeah, there are libraries that do that. I'm drawing a blank at the moment, but it's actually built into PostGIS. You can say, simplify my geometry by some tolerance, and it will literally remove vertices, greatly reduce the file size, and especially if you're talking about a small scale map where you're zoomed way out, you don't need all that resolution, so that's something I would look at too.
You mentioned that quad trees are only good for point data, which I found a little disappointing because now it makes me feel like I've been wasting my time on something. Using quad trees, it's possible to define, if you say A, B, C, D as your 4 quadrants, you're able to define bounding boxes at arbitrary sizes so that you can do a linear search using, for instance, regex in order to just look at the very beginning and determine whether or not something falls within that bounding box. I know it's not strictly a quad tree, but am I going down the wrong path hopelessly? I mean, am I missing something here?
Well, I mean, what kind of data are you trying to index? Is it point data?
No, polygon, anything. Polygon, multi-part, anything.
I mean, the essential thing that you're doing with the quad tree is you're trying to reduce the number of dimensions that you're querying against, right? So I think what you're talking about can be made to happen with a lot of work. I would look at an R tree as a substitute instead of trying to jump through all these hoops to sort of fit your mental model of the data you're working at into the quad tree. I know there's been a lot of research in how we, especially on like distributed systems, like these indexes only really work and make sense if you're talking about one node. And what would it be to like index data across multiple nodes? And so a lot of people are looking at dimensionality reduction, quad trees, geohash, that sort of thing. So there may be research out there that kind of gets to what you're talking about, but if you can get away with it, I would say just use an R tree.
Sure, I get the real reason would be that now you get into a parallel map reduce index search so that you can split up and index across many things, and besides it's fun to reinvent the wheel.
Right.
Hi, I had this map app in mind, and I was wondering if there was a JavaScript. No. So I have this map app in mind, and I was wondering if there's this JavaScript library that does what I'm thinking of. So like say you're panning around and you want polygons to load dynamically kind of behind the scenes in an intelligent manner, caching in JavaScript and only grabbing the deltas you need through say like AJAX. Is there any kind of like JavaScript library that makes that sort of thing easy?
I'm not sure. I would look at OpenLayers because it has such a rich feature set of functionality, but without knowing more about your application.
Well, I was
have you looked at what have you looked at so far?
I haven't looked at anything. I was just thinking about this, and it sounds definitely doable, but I was like, oh, there's definitely some tricky things in there, and I was thinking there's probably someone's already done this
Right.
to some extent.
I don't know. I mean, maybe we could talk after about
Okay.
some options.
All right.
As a quick and dirty, I've got various shapes that are in raster form. What would be the best tool to be able to overlay it onto something and or apart from that, create shapes from scratch where you really got to draw them in?
So you're saying I've got some rasters and I want to get vector data from it?
Yeah.
Or an overlay?
Yeah, in other words, I've either got them in paper form or I've got
Yeah.
them in some
Sure.
non-usable form. I can look at them, but that's all I can do with them.
Yeah, like sort of broadly, this topic is called like geo-registering. So the idea is that you would take, if you have a known coordinate space and then you have your map, whatever it is, like a scanned object or something, all you need to do is define 3 points on it and it will wrap that, it'll make that raster fit the underlying coordinate system. And there's something called Goodle Wrap, GDALWRAP, that does this automatically. So
Is that an open source tool?
yeah, it's open source. It's part of the Goodle family of
Or part of Google Wrap?
Goodle, GDAL. Find the name here. The first one.
Hi, how do the data structures behave when you want to query a polygon that goes, the line on the Kiribati Islands where the plus 180 and minus 980 are the same line? So the fact that the Earth is a sphere and not a rectangle.
I'm sorry, I didn't follow. Can you repeat that? I'm sorry.
The longitude plus 180 and minus 980.
Oh, you're talking about the date line?
Yeah.
Basically, the long and the short of it is that we define longitude to be between minus 180 degrees and plus 180 degrees. So if you have geometric objects that span that, and this is the international date line in the middle of the Pacific, your mathematical calculations or whatever can blow up. But most applications these days you can configure to recognize, say, basically like international date line equals true. So a lot of libraries will expose that as essentially a workaround.
All right, thanks.
Yep. All right. Thanks, everyone.